Containers and Docker, explained in just 5 minutes. In a traditional deployment, applications run directly on hardware with an operating system. Each application, for example, let's say a Spring Boot service, a PostgreSQL database, and a React frontend, come with its own dependencies, libraries, and OS requirements. When multiple applications run on the same system, dependency conflicts can arise. Some applications may require specific library versions, while others depend on different ones. For example, one Spring Boot service might require JDK 17, while a legacy service still requires on JDK 11. These conflicts lead to a dependency hell, making upgrades, maintenance, and system stability increasingly difficult. To solve this dependency hell, containers provide a way to build, ship, deploy, and scale applications independently. In a containerized setup, you still have hardware and an operating system, but on top of it runs a container engine like Docker, which we'll discuss shortly. This engine creates containers that package applications along with their dependencies and libraries. Since everything is bundled together, containers can move seamlessly between machines without compatibility issues, ensuring consistency across environments. Containers act as isolated sandboxes for running processes. Unlike virtual machines, they don't include a full operating system. Instead, all containers on a host share their host's OS, more specifically its kernel. The kernel is the core of an operating system. Much like a car engine, it manages applications and hardware resources such as memory and CPU, ensuring efficient operation. Every operating system has its own kernel. These kernels have different APIs, which is why a Windows application can't run on Linux. It relies on the underlying OS kernel. On a Linux machine, only Linux containers can run because they depend on the Linux kernel. On Windows, however, both Windows and Linux containers are supported. This is because Windows 10 includes a custom-built Linux kernel, allowing it to run Linux applications natively. What about macOS? macOS has its own kernel, different from Windows and Linux. Since it doesn't natively support containerized applications, Docker on macOS runs Linux containers using a lightweight Linux virtual machine. So now let's talk about Docker. To run an application with Docker, we first Dockerize it, meaning we make small modifications so Docker can manage it. This involves adding a Docker file, a plain text file with the instructions that tell Docker how to package the application into an image. A Docker image includes everything needed to run the application, such as the runtime environment, application files, third-party libraries, and more. Once the image is ready, we tell Docker to create a container from it. A container, as mentioned earlier, is an isolated environment with its own file system provided by the image. Docker then runs the application inside the container, allowing us to execute it seamlessly on our development machine. So now let's look at how Docker's components communicate internally. When a user sends a request, such as running, pulling, or removing an image, it first goes to the Docker client, or the Docker CLI. The client then forwards the request to the Docker Daemon, also called the Docker-D, which is the core of the Docker platform, handling all operations. The client and daemon communicate via the REST API. The daemon exposes endpoints that the client interacts with to manage containers, images, networks, and data volumes. Now let's take a look at all the key components of Docker and how they interact with each other using a high-level architectural diagram. This will help us to understand the full Docker workflow. As we mentioned before, when we talk about Docker or Docker engine, we're referring to a client-server application which consists of two main parts: the Docker daemon, which is the server-side component, and the Docker client, which is the client-side interface. At the heart of the setup, we have the Docker host, which runs the Docker daemon. Inside the Docker host, under the control of the Docker daemon, there are two key components: container images and containers. The daemon is responsible for managing these containers, images, and other Docker resources. It also provides an API that allows the Docker client to communicate with it. There's also another important component that we haven't discussed yet, the Docker Registry or Docker Hub. This is where Docker images are stored, either privately or publicly, so they can be shared and reused. The Docker client can be either the Docker command line interface or Docker desktop, which provides a graphical interface for managing containers. So now let's go through how everything comes together in a typical Docker workflow. Before we can run a container, we need to have an image on the Docker host. One way to do this is by downloading from a registry. For example, in the context of Java software engineering, we might work with images like an OpenJDK image and a Spring Boot application image. So in this case, we can use the docker pull command via the Docker client so that the Docker daemon will then fetch the requested image from the registry and store it locally on the Docker host. We can also build custom images by using the docker build command, also via the Docker client. This process requires a Docker file, which as discussed is a set of instructions creating the image. The client sends the Docker file to the Docker daemon, and the daemon builds the image accordingly. Once we have our images on the Docker host, we can use the docker run command to start a container. The Docker daemon will take the selected image and create a running instance of it. The difference between an image and a container is that images are read-only, whilst containers add a read-write layer, allowing applications to run and store temporary data. Once these containers are running, we can manage them in different ways by starting, stopping, and restarting them as needed. If we create or modify an image, we might want to store it in a registry like Docker Hub, so that others or even our own infrastructure can access it. This is done by using the docker push command, which takes an image from the Docker host and uploads it to a Docker registry. Now, everything we've discussed so far describes a single Docker host setup, but in real-world applications, things operate at a much larger scale. We might have hundreds of hosts, thousands of images, and even more containers running simultaneously. But no matter how large the system gets, the overall architecture and workflow remain the same. So in summary, Docker provides a structured way to build, distribute, and run applications efficiently, whether on a single machine or across large-scale cloud environments. If you enjoyed this video and found it helpful, don't forget to like, subscribe, and leave a comment below. Thanks for watching, and I'll catch you in the next one. Bye for now.